Alright, you guys, another tinkering update. Sorry I haven't made any differential geometry videos in a while. I get no views on my videos. I never really have, besides a few of the big topics in the differential geometry reading streams, but anyways, I don't care at all. This is the big update, okay? So I finally got my diametrically polarized magnets. And as proof, I'm going to show you guys, I've got one on the tip of this screwdriver here. I got 25 of them in the mail. Thanks, Digikey. Also, I will say, don't use buyneomagnets.com. Said it got delivered. It wasn't delivered. Digikey all day, every day. Okay, anyways, so I slapped one of the diametrically polarized magnets on the axle of my motor. The problem I encountered was that my magnetic angle encoder was having a lot of electromagnetic interference, a lot of EMI from having the ADC and the stepper motor all plugged in. Because previously, I don't know if you probably don't because you haven't watched my tinkering vlogs, but that's okay. I'm going to catch you up. The last thing I did was I had the motor and then the coil plugged into the ADC. So motor plus ADC, which is the coil, but it's basically the two electronic components are the driver for the motor and that ADC plugged into the ESP32 dev board. So then I unplugged the coil and I then plugged in the magnetic angle encoder, which I didn't have before. And I'm like, okay, I'm going to try the diametrically polarized magnet on there. So first I still have the magnetic angle encoder just freeballing in outer space. And I would say, okay, can I turn on the motor, have this angle encoder going, and then I'll hold the magnet up on a screwdriver and then just turn it near the chip and see if I can just get the reads, without doing anything. And long story short, no, I did not, because of all that EMI. And so a lot of tinkering later, I ended up having to change how I was driving the stepper motor by tying it to a hardware clock on the ESP32, adding pull-up resistors and all this stuff on my, SCL and SDA lines on my magnetic angle encoder here to reduce EMI, all this stuff, okay? But finally, I'm getting outputs where it looks like I'm getting the angle sensitivity, the actual action that I want from the diametrically polarized magnet, and I'm going to show you guys here. So these polos, the microphone will sag away from my face, so hang on, I gotta set this up here. Okay, this is gonna focus better. So I've got my magnetic field finder here, and there's a little bar magnet on a gyroscope basically. Right now the south end of that magnet's aimed towards my diametrically polarized magnet supposedly, and to confirm, when I rotate the screwdriver, it flips around. Boom, flips around. Flips around. This is how I know that this is diametrically polarized, okay? If we're head on here, this focuses, it's probably not, it's probably too close, whatever. You can imagine, okay, there's a circle here, diameter north-south, okay? That's what's going on here. Okay, the difference is I have this magnet here, which is what it came with, the magnetic encoder came with, okay, not diametrically polarized. See how now it's the magnetic field finder is now vertical because the magnetic field is through the pole, right? So you could imagine there are circles going through here, right? So this, and then if we turn it right like this, turn the screwdriver, it's not flipping around north-south, okay? Because the magnetic field is through the pole here. So this is just a normie magnet that you would use for sticking stuff on a fridge. This right here, this special guy, this is what I need. Whoops, see, like that? See how it's sticking to the side of the magnetic field finder? This is like all blurry as hell, so I'm just gonna cut the crap out. We're gonna get to the real deal Holyfield here. So, but these magnetic field finders, this is like a really good tool to like test this stuff, you know what I'm saying? Anyways, I'm gonna stick it back on the screwdriver here because now we're in VS Code, okay? I don't need to have VS Code running right now. I'm gonna do a screen recording. Whoops. What did I just do? We're gonna record. Okay. Anyways, magnetic encoder, angle encoder, screwdriver. I don't need VS Code running in order for my apparatus to turn on now. Okay, I've got my power, 12 volts. This is on USB. I was just flashing the ESP32, so I really don't need this connected to a laptop. I could have this on a power supply, but that wouldn't be able to give me the data if it were just in like a, you know, USB wall hub. So really it does have to be plugged into a laptop if you want data out. Okay, got my encoder handy. I want to show you this. So now if I turn this on, okay, it's going really slowly because I don't want to make things go crazy. This attachment should be on the back of my stepper motor, but I just want to have the code running because now if I do a monitor call, idf.py monitor, okay, it's connecting to the chip. All right, now it's collecting a bunch of zeros and it's got all these timestamps. Oh, now it's erroring out. Whoa. Because my ground just came off. That's probably fucking why. Okay. I need to make sure that everything's plugged in. Okay, let's try and monitor again. Okay, it's running. Great, no problems. Bring the magnet close, and now, boom, look at that. Look at how we're reading all the way from 0 to 360, right? If I'm being really gradual about moving this. It's kind of tricky to hold it in the right spot, but before I would get a range between like 310 to 360 degrees in here. If I just hold it, all right, we're hanging out at 140. Let's go close to like 0 or try 0, 3, you know, let's get a range, okay, close to 0, so a really low number here. Now let's shoot up to like 200 and just like hold it. Okay, so that's just to show that the sensitivity is way better, because now if I use the dumb magnet, right, and I'm just going to slap this on here, I bring it close, okay, not as much range, I feel like. It's kind of, whoops, got the magnet stuck to it. Actually, now that I say that, that's not true. But in the enclosure, it was not doing so hot. So, I don't know, this is just kind of like ruining my own credibility. But okay, yeah, so I'm like spinning it and it's like kind of just hanging out in like one range. If, you know, if I slightly tilt this, it's kind of a misleading demonstration anyways. Obviously, this is not precise, having a screwdriver and just holding it up here. So you know what I'm gonna do is now I'm just gonna hot plug this bad boy onto the back, live onto the back here, and we're gonna see what the output is. Okay, and I'm gonna remember not to unplug the electronic connections here, okay? So I'm just gonna, because now it should be, you know, fixed, flat, and at a fixed distance away from the chip, okay? And it should just be going constantly through 0 to 360. And what do you know? Boom, comes back around on time. That's what I'm talking about. 180, 270, 360. 90, 180, 270, 360. So, and that's partly also why it helps to have the low speed going right now, is because I'm still working out the kinks as far as the data collection goes, like what rate I need to be reading the angle, blah, 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 all that kind of stuff. So obviously, you know, the coil right now is unplugged. I was also getting, last tinkering update, I was using LT Spice to simulate the circuit that's on my op amp, because with this magnet and this coil, the real signal was only an amplitude of positive, negative, plus or minus 10 millivolts. So I wanted to like amplify and then DC offset raise that signal so I have like a bigger signal to be picking up in the ADC. That way, you know, you can do maybe some FFT, do some noise calculation, hibbity hoopla after. Like, it's harder to do that when you have like a really tiny sample with like not a lot of points and it's really narrow, right? So I was like, okay, I'm gonna use the op amp. But the simulation in LT Spice got it up to like, what did I say? Between like 280 and 320 volts, something like that. It was like 50 millivolts amplitude, and then it was raised up by like 275 millivolts or something like that. Okay, well, turns out I did not get that much DC offset. I only got it up like another 20 millivolts, and the peak to peak was maybe like 20 millivolts instead of like 50. So there still is more to tinker around, probably because I connected the coil initially to a multimeter, and then I just like took the video and I'm like looking at what the values are approximately on the multimeter. So like the multimeter can only change so fast at reading, you know, this AC signal, right? And so I probably like estimated, oh, it's between negative 10 and 10 millivolts. Probably estimated that wrong. And I probably have to boost it more and all this stuff. But anyways, that's the update. As I got the magnets, I'm getting good angle encoder reading. And then it's also, the motor is smoothly rotating now, because when I first turned it on, trying to like, you know, get all this stuff to work, it would be just like super choppy from like having a single while loop running. That would be like, okay, while true, we're gonna do 200 steps and then collect the angle, go back, do 200 steps on the motor, collect the angle. Now I'm like, okay, the motor driver is an independent task, and the angle encoder, angle collection is an independent task, and those are just, you know, on their own threads, I suppose. I don't know if there's multi-threading on this ESP32, so I'm not exactly sure on how the hardware is handled, but it's effectively, it's the same in principle from what I understand, as like independent threads that are running, instead of it's like one serial loop that's like, okay, we're gonna do the 200 steps on the motor, okay, stop, wait, and now, you know, beep, do the angle encoder, collect that back, okay, now go back to the top of the while loop. That's dumb. That's a stupid way to do it. You have to do parallel threads. So this is progress. I also shaved the bottom of the protractor. I don't know if you noticed. I shaved the bottom, right? So now the magnet is way closer to the center of the coil. I also have the Hall sensor underneath here, but it's not plugged in. I got a bunch from my Digikey order. That's the other part of the update, is that I'm gonna have this whiteboard here, this poster board, and I'm going to put multiple sensors at once and then have the magnet in one position, instead of like putting the magnet in one position and having like one Hall sensor and then moving the magnet to different distances, angles away from that one Hall sensor. I can just have multiple connected at once, one magnet, simultaneous data acquisition in order to determine how far away do I need to put these Hall sensors, singular, plural, I don't know. How many am I going to need to get a solid read on what the magnetic field is inside of that coil as this is all going on? But hopefully my blurry demonstration wasn't too shoddy on, you know, why the different magnets make a difference, but this is progress. This is a successful end of the day. It's 7:20. I've been just cracking away with what time I have in these afternoons and evenings here to get this all, you know, just like sprinting over to the post office, getting the package, getting over here, coding, cranking it out. Time to go to sleep so I can wake up early and go to the gym early before I have to get stuff done. Taking care of business during the day. Tomorrow's Friday. Let's go.